Hi friends, welcome to this class. So we were discussing about the stereochemistry of sulfur compounds, right? So let us continue with that, right? So here are the few reactions which tells the stereochemistry of this sulfur also, right? So here I have a molecule like this, yes, a double bond O CH3 we can write it as Me also. Me means methyl. C6H4 at para position to this benzene ring we have methyl, right? So if I write like this, you should understand the structure of it. So here if you see 1, 2, 3, 4, 5, 6. So 6 lone pairs are total 6 valence electrons of sulfur, right? So here 6 electrons 1, 2, 3, 4, 5, 6, right, of sulfur. Not I am not counting of oxygen or this methyl, right? So this is the structure. If you see, this is A, this is B atom, oxygen, this is C atom, and this lone pair D. So all four are different, so it will be optically active, and they checked it. It used to rotate the plane polarized towards right side. So dextrorotatory, we denote it by plus. When we react this compound to this Et thrice O BF4 plus like this, right? When we reacted with this compound, it formed this thing. So other things remains as it is. Paramethyl C6H4 sulfur. It was double bond O. Now it became OET. Right. OET it became. This methyl remained as it is. Methyl CH3 and lone pair as it is. And overall, I told sulfur, if it forms 3 bonds, then sulfur gets positive charge. I can write positive charge on sulfur, or I can write positive charge like this. And this BF4 minus, right? So this is the compound it formed, right? Further, when this was first treated with Et twice CD means cadmium, and the second step with HBr, they got this product. Other thing remained as it is. Paramethyl C6H4 which is attached to sulfur. Here OET was replaced by ethyl, right, and methyl remained as it is, and lone pairs as it is, right? So since it is 3 bond, so here plus charge, let me write it here only, and here the anion is Br minus now, so it is Br minus, and it is also optically active because see 1, 2, 3 and 4 all are different atoms, so it will be optically active, right? Yes. So when they checked the optical activity, they observed that it is Leo rotatory. It used to rotate the plane polarized right towards left side. So initially it was plus. After this reaction, it got this intermediate, and this intermediate treated with these two reagents, we got this product. So from plus to minus, the reaction has happened after all this step. So such kind of reaction we call it as inversion. What inversion? Stereochemistry. Initially it was plus, now it is minus. Inversion of stereochemistry. Stereochemistry has happened. So this is the reaction they will ask in your exam. So you should remember this, right? And one more thing. So see, here I have R1, here I have R2. Valence of sulfur will be 6, right? So here it is 1, 2. This electron comes from this R1, and this electron comes from R2. So I am not counting that, because one bond means 2 electron. One will be shared from sulfur, and other will be shared from this R group, right? So let me count only of sulfur. So 1, 2, 3, 4, 5, 6. Like this, 2 lone pairs will be there and 2 bond pairs will be there of sulfur, right? So these things we have studied, right? To this, if I add some oxidizing agent, just a minute, yeah, to this if I add oxidizing agent like peroxides RCO, if it is OH, acid you will call. Per acid means just OH. So there will be extra oxygen like this, and it is O bond. This bond we call it as peroxide bond. That bond will be very weaker. This bond will be easily cleaved. So this oxygen will be electron deficient. so it will react like that. So it acts as a oxidizing agent, so it can easily give this oxygen, right? So it acts as a oxidizing agent. When we do this reaction, so what happens is that, see, here it is optically inactive. Optically inactive means it is not going to rotate the plane polarized towards right or left. So it is optically inactive. Can you tell why it is optically inactive? From plane of symmetry, just see this. So just assume that this is R1 and this is R2. So light blue is R1, dark blue is R2, right? And these two lone pairs are this one, these two lone pairs, right? White represent lone pair. So if I take a plane, so you assume this is a plane, right? If I take a plane, if I cut it like this, see, this sulfur, black one is sulfur, just assume this sulfur will be equally halved, this R1 is equally halved, this R2 will be equally halved, right? So it will cut like this, and see, this lone pair and this lone pair will be mirror image of it, so it will be having plane of symmetry. The molecule one which has plane of symmetry, I told, that will be optically inactive. So this compound is optically inactive, right? So in this way you can assume it, right? So it is same as water molecule, OHH, OHH. So in water molecule its shape is V shape, right? If you see, it will be V shape or the bent shape we call, because while telling the shape, these lone pairs we won't consider, right? So just if you remove these white lone pairs, you will see that it will be like V shape only, but here it is R1 and R2, so different color, R1 and R2, right? So this is how you can imagine, right? So it is optically inactive. So this compound is optically inactive. When I add this oxidizing agent, then what happens? Oxidation happens. So what oxidation happens? So nothing but, see, the oxidation can happen here or here, right? So we will get two products. One is like this, COO, R1, R2 and lone pair here, or other product can be like this, R1 and R2. So those two products. Now if you see the optical activity, see here, this is A, this is B, this is C and this is D, right? All four are different only, right? Here lone pair, here oxygen, here R1, here R2. Right. Since all four substitution of this sulfur are different, so such compound, this sulfur will be asymmetric. Once the sulfur is asymmetric, it has the ability to rotate the plane polarized right towards right or left. So this rotates the plane polarized towards right and this rotates the plane polarized right towards left. So when we take this optically inactive sulfur compound, when we add this oxidizing agent, we will get optically active compounds. But the thing is, we will get in racemic mixture. So this will be 50% and this will be 50%. So plus will be 50%, minus will be 50%. This kind of product we call it as racemic mixture and we donate it by plus and minus. Means we will get racemic mixture here. So this is what I wanted to tell. Right. So these two were the reactions. Right. So I have one more reaction. Let me tell about it. Right. So these are the few reactions of sulfur compounds. I hope you are enjoying the class. Right. Yes. Once we discuss that, so let us discuss this one. So again I will take this sulfur oxide only. See, all the substitutions are different. Here oxygen, here lone pair. These two substitutions is like C6H4 para position methyl, and here I have CH2PH benzyl group. So all are different. So it is optically active, and they saw that it rotated the plane polarized towards right, so it was dominated by plus. To this they added this thing, ET thrice O plus BF4 minus, the same reagent which I used previously. So what it used to do is, see, nothing. This oxygen is bonded to ET, so it will be like 3 bond it used to form, OET like this. Other thing remained as it is. Right, it is C6H4 para position methyl, CH2PH it is below the plane. Since it is 3 bond now, so sulfur gets positive charge. So anion will be this BF4 minus only. So you can write BF4 minus, right, anion it is. Further, to this, if I add any base like OH minus, that is any OH, KOH, any of the base, if I add, I'll get this product. Now what happens? S double bond O, right? So it is CH2 PH. Above plane I'll get C6H4, para position methyl is there to that, right? So initially it was plus. After this reaction we got an intermediate, right? This is the intermediate. To that, if I add a base, again the OH will attack and we will get oxide. Here it was oxide, there is also oxide. But the thing is, initially it was plus, but the oxide which I get is negative now. It rotates the plane polarized right towards left side. So from plus to minus it is changing. Means what it is happening? Inversion. Positive to minus means inversion of stereochemistry is happening. So this kind of reaction is nothing but inversion in stereochemistry, right? So this is the reaction. If you assume, if I take this as a starting material, right, it is negative. To this I will add this thing, ET, this one, ET thrice O plus BF4 minus. So I will get this intermediate, right? Further to this, if I add OH minus, right, I will get this product. So here what happened? Initially it was negative, but now I got positive, right? So this is a reaction in which from here to that side also we can go, or from that side to this side also we can come with the same reagents only, right? So this is the reaction of this sulfur in which inversion of stereochemistry happens, right? So this one reaction you need to remember. Once we discuss these two reactions, I am left with only small concept. So before going to that, let me write it here only. I have some space. So this one, sulfur I have double bond O. Here I have same C6H4 para position methyl, and below the plane I have O C10H7 and 1, 2, 3, 4, 5, 6. Yes. So this is the thing I have. To this I will add Grignard reagent RMGX. Here they are using Grignard reagent, that is methyl magnesium bromide. Methyl magnesium bromide. So it will be more of ionic character than covalent character. So we can write negative on methyl, positive on magnesium, right? As it is electro positive metal, right? So what happens? So here we have this OC10H7, right? So it is a good leaving group. As soon as this methyl CH3 minus attached to this sulfur, it loses the system. So we will get this product. Yes, double bond O methyl and C6H4 para position we have again methyl, right? So if you see, it is optically active as it is attached to different substitutions A, B, C, D. So they checked the optical activity, it was plus, but later they got this product. They saw that after this reaction they used to get this product which is racemic mixture, as I have discussed, plus minus. They used to get both the product, positive also they will get and negative also they will get, but both product in 50% of plus, 50% of minus. So we will get racemic mixture, that is represented by plus or minus, right? So this is the reaction you have studied, right? You know these all reactions now. So let us see few more concept and let us wind up this stereochemistry of sulfur compound, right? So you know about ketene. What are ketene? Ketene are nothing but carbon double bonded to another carbon. That carbon is double bonded to ketone group, right? So this is ketone, you know, C double bond O. Here I can have CH3, here also I can have CH3. This is ketone. Since it is CH3, we call it acetone, it is, right? But ketene is C double bond O is there, but that is doubly bonded to one more carbon which can have any some R or R dash here like this, right? So here if you see the hybridization, it will be sp2. Here if you see the hybridization of this carbon, it will be sp, right? So this we call it as ketene, and the valency of this carbon is 4. So it can form only 4 bonds, 1, 2, 3, 4. because 1 electron, 2 electron, 3 electron, 4 electron, valence is 4. Whereas sulfur, we have sulfine. We have got sulfine. See here, for example, the sulfine I have is C double bond S double bond O. But this sulfine is there, right? Here I can have R dash. This is sp, so it should have linear in shape. Linear. But here the sulfur, the valence is how much? Here the carbon valence is 4. But with sulfur, the valence is 6. 6 means here see 1 electron, 2 electron, 3 electron, 4 electron, 5 and 6 electron. So there will be lone pair of electron. If you see the hybridization now, so to check the hybridization, what is the formula? Count the number of sigma bonds plus lone pair of electrons. Here sigma bond, 1 sigma bond, 2 sigma bond and 1 lone pair. So 1, 2, 3. 3 means it is sp2. Right, sp2. Right. So this sulfur the hybridization is sp2. So sp2, right, and because of these lone pair bond pair repulsion will be more. So the shape will be not in linear, it will be like bent shape, because sp2 means trigonal planar, right? So here if I have central atom, it will be trigonal planar sp2. But to tell the shape, we never consider lone pair, right? So it will be like this, R dash. Lone pair will be like this, right? So it will be bent shape, or it can also be like double bond over here, lone pair can be here. So because of which, and see here, if you see the hybridization, this is also sp2, this is also sp2. So all will be in a same plane. So if I take a plane, all are in single plane. If I take one more plane, if I cut it, all atoms will be equally hard. So these molecules will have plane of symmetry. Since these have symmetry element, they will be optically inactive. So they will be optically inactive. Since they are optically inactive, right, and these have sp2, so they have geometrical isomerism. They show geometrical isomerism, right? So these are optically inactive, but they show geometrical isomerism. So that's the thing I wanted to tell, right? So let us see few examples in which they show the geometrical isomerism, right? Yes. So if you see, I have this compound, benzene ring attached to carbon. I have one more benzene ring. At para position I have methyl. I have double bond S here, sulfur, double bond O. Right, I have this compound. If you see, this is the lone pair here. Lone pair mass will be very less. I mean, it doesn't have mass only. If you want to tell, its mass will be very, very small. That is in EMU. So this is the bulky group, and within these two, this is the bulky group. Both groups are opposite, so it is E isomer. E geometrical isomer. Alright. So these things you should know. If I tell E isomer, you should understand that it is geometrical isomerism. If I have the same compound only, but now the double bond O is here, and these things remains as it is. Para position methyl, and here I have simply benzene ring. So now if you see, both bulky group are on same side, so it is Z or Z isomer or Z geometrical isomerism. So this is what is nothing but this sulfine, right? So this is the stereochemistry of sulfur, right? So what we all understood, if I have any central atom, it can be sulfur, nitrogen, anything. If 4 substitutions are present on those central atom, then that will be optically active. They will show optical activity, right? So, but scientists, they could resolve some of the compounds. Those compounds, if they resolve, they check optical activity, then only they will tell whether it is optically active or not. Otherwise, they won't tell. They will tell they couldn't able to resolve it, right? So those compounds which are in planar, like sp hybridization, sp2 hybridization, such compound doesn't show any optical activity because they will be having plane of symmetry or any of the symmetry elements. So those compounds will be geometrical active, means they will show geometrical isomerism, that is cis and trans. They won't show optical activity, right? So all these things we have discussed from first to this class, right? So I think this is the end of the chapter stereochemistry other than carbon. I hope you like these videos. If so, please share with your friends, and don't forget to like the button. And if you are not the member of this channel, please subscribe it and share with all your friends. Share love, and thank you.